Okay, this video is going to look at polar molecules and what makes a molecule polar. Well, polarity in a molecule is caused by an unequal sharing of electrons between atoms. And notice a difference between a polar molecule and a polar bond. And electronegativity, which we've seen before, is a tendency of an atom to attract shared electrons. And we need to emphasize shared electrons. And anytime two atoms of different electronegativity values share electrons, there'll be a partial negative charge on one atom and a partial positive charge on the other atom. And of course, the more electronegative element will have the negative charge. So, molecule polarity. A dipole is anything with a positive end and a negative end. So if a molecule has positive and negative ends, it's going to be polar. Another word for a dipole is polar. A bond is a dipole if it contains different atoms. Clearly, any two different atoms or different elements will have different electronegativities. A polar molecule is a molecule where the polar bonds are asymmetrical and not symmetrically arranged, so the dipoles do not cancel. If the molecule is polar, then of course the dipoles will cancel. And a non-polar molecule is a molecule with no polar bonds, or a molecule where the polar bonds are symmetrically arranged. So a molecule can have polar bonds basically, but the bonds will cancel each other. The dipoles will cancel. This is an example of a polar molecule. The dipole moment is a measurement of a molecule's polarity. So the H is going to be delta negative, so delta positive, sorry, and the Cl is delta negative. Determining the molecular polarity. Dipoles are asymmetrically arranged and do not cancel in this bent arrangement in the water molecule. So a water molecule has a bent structure. We're going to look at molecular shapes later on. And determining molecular polarity. And a polar molecule has symmetrical charge distribution resulting in a positive and negative end to the molecule and a net dipole moment. So in this case, you have 3 chlorines and a hydrogen. These are tugging in different directions. But for the hydrogen, this is what the electronegativity is pushing towards the carbon atom. And therefore, there's a net dipole moment. BF3, however, fluorine is a lot more electronegative than boron, but there's going to be no polar molecule because the forces will cancel each other out. The F is more electronegative, but the molecule is nonpolar due to its symmetrical shape. The dipoles are symmetrically arranged and cancel out. This molecule, however, NF3, will have a dipole because all of these are pulling downwards. And therefore, this time, because the molecule isn't flat, there'll be a net negative, there'll be a dipole moment. No dipole moment in carbon dioxide because the delta negatives will cancel each other out. But water, there is a net dipole. Similarly for SF4, again, we're going to look at these shapes later on. There is a net dipole. And for CH4, no net dipole. CH3Cl, there is a net dipole. Same thing for CH2Cl2, CHCl3, and CCl4. Then move on to bonding. The bonding in I2 is covalent. The structure is simple molecular. It has a low boiling point because the intermolecular forces are weak. And note the regular arrangement of a solid. So it does in fact form a lattice. So iodine molecules will form a lattice. You can see it here. The cube where you have 4 molecules in the corner, 1 in the center. And then in the middle of the square, you have the middle of each square, you have an iodine molecule on each face. And then ice also forms a lattice. It is less dense than its liquid counterpart, because hydrogen bonds are longer than van der Waals forces. And water has this structure here. And it has a higher melting point than expected, because hydrogen bonds are stronger than other intermolecular forces. Then this is silicon dioxide. Its structure is similar to diamond. It has a high melting point, because it requires a strong you need to break covalent bonds in order for it to melt. And then again, sodium chloride, we've done this before. The compounds have high melting points because of the high electrostatic forces of attraction. And then the metallic bonds in copper. We've done copper before. The specific definition of a metal bond is that the metal, like copper, is the attraction between delocalized valence electrons and the nuclei of the metal atoms. These electrons hold the copper atoms in place, and therefore the more valence electrons you have, the stronger the metallic bond. And also the smaller the ion, the cation, the stronger the metallic bond. So these electrons head towards the positive nuclei of the nearest copper atoms. And there's a YouTube video for you to watch.